All right. Heavenly Father, we thank you for this day. Thank you for these students. Just pray you to help us use this time wisely to prepare for the test which is upcoming. I pray that the students would get rested and just collect their thoughts, Lord. In your name I pray. Amen. So I will collect your homework binder at the end of class. I said it was due today, but since you might want to look at it while we're talking, just let you hold on to it. But don't let me let you leave here today without giving me those binders, because I don't want you working on it right up until the moment of the test, if possible. Now, that's not always possible in here because of the schedule, but this time, since we bumped it a week back, we have that luxury. Okay, before I forget, this problem, es no bueno, is no good. Because, you know, I think I said announcements about this, but, you know, there's a very problematic problem because, yeah, so I guess part A is okay. I think that's the center. That's the center of D6, yeah? Is it? Oh, wait a minute. Isn't even that okay? I don't know if that's not even.
I don't think anything's okay.
No. I mean, if I had 1 and A cubed, I'd be okay with that. That would be the center. The center's a normal subgroup, right? If you have a dihedral group of even order, the 180-degree rotation, so to speak, a to half the power, right? If it's that will commute with everything because of the way the generators and relations work. But this is not that. This is a subgroup which is not normal. And since this is a subgroup which is not normal, these calculations are meaningless. All right? You cannot calculate products of the factor group when there is no factor group to calculate products in, right? So, or at best, I shouldn't give one value. I should give several possible values. I don't even know how to start interpreting it. This is a ill. It's not right. Again, because I can only talk about the factor group when K is actually normal, and this begs the question of looking at calculations in a factor group which does not exist, which means that there's one or more typos here. I'm not sure which one's the typo, or if it's just altogether wrong. Anyway, is it important to be able to calculate the order of elements in a factor group? Yes, but it should actually be a factor group. How do you decide whether or not a factor group is actually as advertised? What important thing do we need to know about the quotienting group? What's that? The subgroup must be normal, right? Which means what? How do we define normal? Right and left cosets are equal for all representatives, right? Alternatively, and more conveniently often, that the subgroup is closed under conjugation, right? That G inverse is a subset of H again. That gives us normality of H. But that's not the definition. That's just our go-to test in here. In a different book, that might be the definition. All right, well, I got to get that on my system. You guys have questions?
What sections is the test on?
What sections is the test on?
I know there was a question
Well,
about section 8.6 on the training.
So I threw out the combinatorics question because I just didn't care for the textbook on that section. I read it 2 or 3 times, and it never quite made sense to me. And it has made sense to me in other books, so I thought, it's just better not to cover that for you guys since I'm not happy with the textbook's presentation. So we skipped the combinatorics application of the orbit stabilizer.
So that's a freebie.
Yeah, that's a freebie. On the other hand, we have covered the example in class counting the how many isometries there are of a cube, right? So that would be a legitimate test question, even though it's not in the text.
I mean, that was more of a 2.7 question, I think.
Yeah, but the counting came from the orbit stabilizer theorem. So it's, in some sense, it's the application of section 8.3 to 2.7. But there's deeper counting stuff in section 8.6 I've never talked about in class, and that I would not test on. So if I did test on something orbit stabilizer counting kind of stuff, it would probably be something like the cube or, you know, something of that nature, and or just the class equation in all of its various nefarious ways, right?
What about rings? Anything on rings?
Rings is not on the test. No, this is, we froze a moment in time. No momento. So so this test covers cosets and Lagrange's theorem, normal subgroups, factor groups, vector groups, the isomorphism theorem, products and factors, Cochise theorem, group actions, the CELO theorems, but this we omitted. So now let's see here. What's the difference in these sections? Pretty much everything in sections 2.6, 2.8, and 2.9 is fair game. 2.10 too. Like there's, I think, pretty much no stone unturned in those sections. We proved most of the theorems in there. You probably should be able to prove them. Section 8.1, well, I proved some things in there, but not everything. You should be aware of the results, and if I tell them to you, I'll be able to do something with them. Like, you know, maybe you should be able to prove that if you have that H is normal and K is a subgroup, then, oh, I forget. But we had a whole bunch of those theorems. I left my book at home because I'm an idiot. But I'm trying to remember, there's a whole bunch of different theorems about taking products of subgroups and getting the product group HK and the properties of that product group and how it's isomorphic to other things. I've not proved all of those things, but I proved some of those things, right? So, of course, if I proved it in class, it's more likely to be directly tested, and or if you had a homework on it. Cochise theorem, of course, you should know the statement of. There are some. I mean, we covered these sections more lightly than those ones, right? So like chapter 2, you need to know backwards and forwards and upside down. Chapter 8, you need to be aware of the results and be able to apply them where problems like the homework. Like CELO theorems, I don't expect you to be able to prove them, but I do expect you to be able to apply them, right? So we just really had 2 or 3 different homework problems that applied them, right? And we had like an in-class example. What was the class example we had? If the order of the group is PQ, where P and Q are primes, then it's what? It's not simple, right? There was that problem. What's that? Yeah, order, if the group has order PQ. What does Cauchy's theorem say? It says if you have a group of order P, what is it? No, that's not it. If you have a group of order P, what can you say about the group?
Cyclic.
It's cyclic, right? How would you prove that? This is one of the 5 corollaries to Lagrange's theorem you should be able to prove, right? If you have a group of prime order, suppose you got a subgroup. Well, pick any element, right? Look at the cyclic subgroup generated by that element, non-identity element. That's a subgroup of the group, right? Because Lagrange's theorem, the order of that subgroup has to divide the order of the group, but the only possible divisors are 1 and P. It can't be 1 because it's already got 2 things in it, 1 and the identity. It's going to be the element and the identity, at least. So it has to have order P. Consequently, that's a generator, right? In fact, you can make that same argument for any non-identity element of a group of order P. So if the group has order P, it's cyclic, and every non-identity element's a generator. That's true. But if P divides the order of the group, that's where Cauchy's theorem comes in, right? If P divides the order of the group, Cauchy's theorem says what? There must be a subgroup of order P.
I think it's any P to the K that divides.
There has to be an element of order P, I think is what it says. Yeah. There exists an element of order P, which is tantamount to saying that there exists a cyclic subgroup generated by said element of order P, so we don't disagree.
Having an element order P is stronger than having a subgroup order P.
I suppose so, because I'm saying it's a cyclic subgroup. But then again, we were just talking about if you have a subgroup, it's a group, right? If the group has order P, then it's automatically cyclic. So, yeah, these are not as disconnected as they at first glance seem. Now, there are some important concepts. Now, you know, now there are things we proved fairly carefully in here, like we proved the orbit stabilizer theorem with some amount of care, right? I proved to you that, I don't know if I proved it, but I said it would be a good test question to prove that the stabilizer is a subgroup, right? We proved that the orbit, the cardinality of the size of the orbit is equal to the index of the stabilizer, right? I think I might have proved, at least I indicated the proof, that we can set up an equivalence relation on the set on which a group acts, because the equivalence relation would just be that two elements are in the same orbit, right? So that defines an equivalence relation, consequently defines a partition of the set. So that allows us to do counting by adding up the number of, if we add up the number of things in each orbit, that has to cover the whole thing because the orbits partition the group, right? So these are things that we actually did in detail, some detail. So I would encourage you to know how to prove the orbit stabilizer theorem. We were fairly careful about proving the class equation, right? That you should probably be able to work out for yourself. But there are harder things in Chapter 8 which I wouldn't tend to test on, right? Like there's a Frattini thing. There's the results about intersections of CELO subgroups as they relate to the factor group or the other thing. Those are a little bit, those would be like bonus if I was to ask something on those. But you should know the basics, like what is the definition of a P group, right? What is that? What does it mean for something to be a P group? A group of order P to the K? That's not, no, that's not.
A group where all the elements.
It's a group, a P group is a group such that every element in the group has order P to the K for some K.
But did we have a theorem that means that it must necessarily have order P?
I don't think that's the case, no.
That's a lemma right after that.
Oh, that is?
Yeah.
It has to have order P to the K?
If G is a finite group and P is a prime, then the order of G is a power of P if and only if G is a P group.
Oh, okay. Okay, I forgot that. I'm sorry. I might have proved it, but it's at this point it slipped my mind. But it's good you guys, at least somebody here studying. Let's see here. Very good. These are problems I like to have. It warms my heart when students know things I don't. That's great. That's the world I want to live in. That does not mean I want to teach mathematics. I'm saying this in a meaningful and good way. Like I feel like I know a little bit about abstract algebra. You guys know more on certain points, then I'm happy. That's great. Although it would be nice if I could remember what I said a week ago. That'd be awesome.
We should know all the isomorphism theorems in 8.1.
Yes, you should be able to prove the first isomorphism theorem. You should understand, like you should wake up in the middle of the night, wake up with a cold sweat and go, oh, the kernel is a normal subgroup. I know this, you know? Like, why didn't I think of that? Have that dream before the test rather than after the test, though, you know? If I ask you to prove something's a normal subgroup and also ask you to prove that some quotient is equal to something else, I mean, what kind of question is that, right? If you're asked two things at the same time, show something's a normal subgroup and show that the quotient of one thing is isomorphic to another thing, that stinks of the first isomorphism theorem. It reeks of it, right? So you probably need to invent an isomorphism.
Like the second and third of the other isomorphism theorems, the ones in 8.1 specifically.
It's good if you're aware of them. If I asked you to prove them, you ought to be able to prove them.
Okay, but we shouldn't expect to memorize them and then like be able to.
I don't think I've had homework which reflects that skill set at this point. So, but I'm happy if that's on your list of things to do. Let's see here. I was getting to a point. CELO theorems. So, in contrast, what's a CELO P subgroup? Every CELO P subgroup is a P group, right? But it's stronger than that, right? It's a CELO P subgroup if the order of the whole group is like m times p to the n, right? And the group you're looking at has order p to the n. And the m does not have a divisor of p in it, right? So like, for example, if you were dealing with a group of order 20 and you found a subgroup of order 4, that would be a CELO 2 subgroup. If you found a subgroup of order 5, that would be a CELO 5 subgroup, because whatever's left over, 5 times 4 is 20, 5 has no 2 in it. In contrast, 4 has no 5 in it, So the CELO subgroup has it has context attached to it, right? Like, it depends on the ambient group whether or not a group of a certain order is actually a CELO P subgroup. It's a relational thing between the total group and the subgroup you're talking about. What are the most important things to know about the CELO P subgroups is the CELO theorems, right? Maybe not even that, though. It seems like the corollary to the CELO theorem is the one that's kind of easiest to remember and most powerful in terms of its application. What is it? So if we have different CELO P subgroups, they're related by what? Conjugation. So if there's a unique CELO P subgroup, it has to be normal, right? So that's like super useful if I'm thinking about like even, you can take that and apply it back to chapter 2 to gain further insight, right? Like we had to struggle, well, struggle is too strong a word, but we actually had to do some calculation and toil studying D3, right? We looked at D3. We found it had subgroups, 1A, A squared. It also had the subgroups 1B, 1BA, 1BA squared. These were the sort of 4 interesting subgroups intermediate to the stupid group and the whole group. And so the fact that there are 3 CELO 2 subgroups immediately tells me that those are not normal, right? But in view of CELO's theorems, the fact that there's just one subgroup of order 3 tells me immediately that that's normal. Of course, there's an easier way to see that, which is that that subgroup of order 3 has index 2, right? And anytime you have just 2 cosets with respect to a given subgroup, it's automatically normal. We proved that. That makes a decent test question. That was on a list of, that's one of the questions I'm debating whether or not to put on the test. But just saying. Anyway, since I'm telling you, it's probably not on there though, right? Let's see here. It's inconceivable. Let's see here. Sorry, my mind starts reciting the rest of the lines. Never go against a Sicilian. Let's see here. Sorry, I digress. Anyway, goodness gracious. We have all kinds of theorems that we have, how do you construct homomorphisms between 2 subgroups? Like, how do you decide how many possible homomorphisms there are? We studied that in some detail. We have given pretty much a complete account of how many homomorphisms there are between ZM and ZN, right? There's some things to think about there. What else? This is the thing so given a subgroup, just proving it's normal, there's kind of a decision you have to make as a student at this point with everything, the tools you have at your disposal, right? There's two main roads you can go down proving normality. The one is to try to find a homomorphism which furnishes it as its kernel, right? The other is just to prove it's normal, right? And almost never, did we ever prove anything was normal by showing that left and right cosets were equal?
I know that we've used the fact that its index is 1 or is
2. Yeah, that's true. So in your mind, that's the same thing.
Seems like usually do the conjugation.
Yeah, I think we've almost, the only place I can remember actually using left equals to right was my stupid first example where I showed you that the left and right cosets of an abelian group, if it's an abelian group, then the right and left cosets of any subgroup are just the equals because you can element-wise commute and convert. You can just rewrite the set of a left and right coset as being the same thing. That was the one and only time I used the definition directly, as far as I remember.
It's just a pain to use the direct definition because you have to do double inclusion.
Yeah. I got away with not doing the double inclusion because I just worked at the description of the set directly, but yeah. Not usually possible to be convincing in that kind of argument. What's your goal on the test? It's to show me that you know group theory, right? Right. Any questions? Question, is linear algebra a prerequisite for this class? Okay, good talk. No, you have other questions, you can ask other questions, I'm just reminding you. It is a prerequisite for this class. this foreboding comment will be more real to you after Wednesday. I'm not trying to get you to go back and study linear. There's no hope for that. You know what you know at this point. Well, I mean, it's a whole course, right? There's what? How many theorems in linear algebra are important? All of them, of course. Let's see here. We have worked some problems with, I'm trying to think here. You have worked problems in your homework about orbits and stabilizers, actually finding the shape of orbits, right? So some of those problems are nice. I don't know. I'm running out of stuff to say here. Would you guys have anything you want to ask me? How many questions on test? I kill you. What? No.
Is it shorter than the last one?
Is it shorter than the last one? Depends on if you know your stuff. I think if you know what you're doing, it shouldn't be that long now. If you don't know what you're doing, then it will be too long. I will tell you this. I actually have you find the Cayley table of a factor group. That's on there. That's hopefully not surprising. Let's see here. There will be a problem which involves the first isomorphism theorem. I guarantee you that. What else will I guarantee you? There will be something on group actions. I will guarantee that. I'm on the fence with CeeLo theorem. See, I got a 5th page. The question is, do I keep the 5th page? You know? I think I should, though.
Make it bonus.
Make it bonus. We should start 5 minutes early and 5 minutes late, just for the sake of extending the suffering. But no, for helping the students. I don't take an adversarial approach to teaching. You guys are. I'm a. What is it? Guide on the side, or something like that. Although if they'd seen Naruto, they'd realize that Sage on the stage is way more awesome than they think. Anyway, you guys haven't seen Naruto, so you know what I'm talking about. Let's see here. No question. You seem like you had there's a question brewing back there.
You said you're not sure about CeeLo.
So you don't want to exacerbate it, huh? Yeah, I hear you. Well, I've told you guys about what I do when I was an undergraduate. Like, I will go and ask pointed questions about things I want to be on the test, but I think other students don't, to try to, like, get them on the test, you know? No? You don't ever do this? It's an important technique. Let's see here. Well, anyway, I hope I have communicated to you that, like, the basic concepts in Chapter 8 are important. The proofs of the major theorems that we've actually spent a lot of time doing in here are important. But there's harder stuff towards the end of each one of those sections that I'm not too fussy if you don't know. Like, I'm much more, make sure you know the corollaries to Lagrange's theorem and how to prove them. There's like 6 of them. They're all pretty simple when you're in the middle of it. But if you just take one, take it out, put it on a blank piece of paper, and see if you can still do it. All right? Yes? Well, we had some in the homework. So let's see here. I mean, I don't think I'll do that, but what I will do is give you some guidelines. So if we have phi is a homomorphism from G to H, and what are some general rules that we can use to locate all the possible homomorphisms? Yeah, what are features? What are features that we expect? First of all, I mean, this is kind of a second order feature, but I'll just get it out of my system. The kernel of that has to be a normal subgroup, right? So that's sometimes limiting, but not so much in my experience. I think the biggest thing is If you have G is generated by, say, X, well, let's say it's generated by X1, X2, Xn, then what you do, right, what you do to those does what? Yeah, that will completely fix the homomorphism. But then you have other rules, right? Like you can't just do anything you want with the generators. You have to send them to objects which have similar structure, right? Like, in particular, the order of phi of x has to be what? Yeah, this must divide the order of x. Another thing, like if you're looking at let me be a little bit more specific here. Suppose you were looking for a homomorphism from, say, D3 to something. Then you would also need this, right? You would need that phi of ABA is what? Right? But on the flip side, this is equal to phi of B, right? So all of a sudden you need these things to be equal. You know, you have to respect relations under the image.
He's looking at like factor groups of G, for instance, and just like looking for isomorphisms from that to H, or like subgroups of H. Is that like a legit approach to kind of doing that?
We have had we have some results, and I don't remember them entirely, but we had a homework problem where we in fact looked at 4 different things that have to be, you know, if we, what were the homework problem was basically like this, right? If we had this and this have property, you know, Bob, then G has property Bob, right? I mean, there was an ABCD homework problem like that.
Finally generated things like that.
Yeah, exactly. If the quotient's finally generated and the K is finally generated, then the group is finally generated. If they both have trivial centers, I think it was, then the group has a trivial center. I forget the rest, but that, if you, I guess that in principle could be used if you're looking at a homomorphism. If you were looking at a homomorphism from say G to G, right? If you're looking at that sort of thing, then
One thing the book seemed to was doing a lot was, because the first isomorphism theorem says that, you know, if you have phi, that's a homomorphism, then G mod the kernel of phi is isomorphic to the image, which is some subgroup of H. So if you just
yes.
picking out those isomorphisms, those kind of provide your homomorphisms on the level of G to H.
So your comment is we should also think about this. So in other words, you're saying, well, that is the first isomorphism theorem. How to say this?
It seemed like it was easier to like find isomorphisms exhaustively than homomorphisms because there's a lot more structure to that. Because you can tell when 2 groups are isomorphic fairly easily. So,
Right. Yeah. I think looking for isomorphisms is actually easier.
that's what I found.
That's my personal feeling, because isomorphism, we don't get that the order of the image divides the order of the element. We have that the order of the image is the order of the element. That's pretty exacting. And this is, of course, useful if I'm thinking about homomorphisms from G. Well, I guess I'm looking for how to say this? I mean, that has to have a bearing on what are possible homomorphisms from G to H, right? You know, I think generically speaking, this is a fairly difficult problem, and there's a lot of like higher order thoughts in this sort of can of worms. I mean, there's some examples we've looked at which have involved observations about the image, the target group, which like, oh, it doesn't have a subgroup of order such and so forth, or you know, it's not abelian, whereas the quotient has to be abelian, or something like that. I mean, but on the other hand, we have completely and exhaustively categorized possible homomorphisms, for example, from here to here, right? Like there's a homework problem where we work out specifically what the possible homomorphisms are, right? What, and so what, and they all appear in the form what? So let's say phi of x sub m is equal to something like k x sub n. I usually use brackets, don't I? Yeah. But the m and the n and the k, they have to play together nicely in a specific way. I'll let you look at the homework problem. And what do we need about, I'm trying to remember, well, of course, the image of phi, I mean, this is sometimes helpful. The image of phi has to be a subgroup of the, the target space, right? So what's that say about, but on the other hand, this is, this is cyclic, right? Is the M cyclic? It's generated by 1, right? 1, 2, 3, 4, all the way up to M. So this is phi of 1, right? And so the size of this has to be a divisor of M, right? Cardinality. So if it's a 1-to-1 map, it's got M things, right? It could be a 2-to-1 map, then it'd have M over 2 things, and so forth. So, if you're looking at, if you got something like Z15, then what are the what possible orders? This could have order what? What are the orders possible for a homomorphic image of Z15? Orders is probably the wrong word. No, I'm sorry. We use order for both things. Order, group order, right? Could have order 1. Could have order, what did you say, 3, 5, or what else? 15. Yeah, them's your choices. So if you're saying I'm looking for, going from Z15 to say Z20, it's fairly clear that you can't achieve the images that have size 3 or 15 because those are not divisors of 20. So the only possible ones you could build would be this or that, right? And it's fairly obvious what those are, right? Phi of x is equal to 0. That's the order 1. And phi of x equals to what? To get the order 5.
4, 8, 12, I think 4, 8, 12, 16 are all order 5.
Say 4x will do it?
Yeah.
Does that have to be 5? Because the number of homomorphisms is equal to the greatest common denominator of the correct elements. So there's the trivial element. Map it to each of the four elements.
So how'd you guys get to 4?
This four
Oh, 20 divided by 5. Okay, very good. Yeah. Duh. Wait, we worked that out in general in that homework problem, right? And we even enumerated how many such maps there were given the condition, right? Uh-oh. It may not have long to live. Well, I'm keeping you guys 10 minutes over next class, so I figure I should let you go 10 minutes early this class, right? It's only fair. Okay. I thought it was nice. I don't know. Disagree with me if you want.